If you're watching this video, you're watching my lesson on mechanical advantage. In this lesson, we'll be talking about what mechanical advantage is and how it applies to simple machines like levers. So if you recall, in our previous lessons, we talked about what levers were, what types of levers there are, and how they work. So as a quick review, you should know in levers, there is the effort, right? Or the effort force, the amount of effort that this person is putting on, the effort arm, the side of the lever or the length of the lever that is having the effort force applied to. And then you have your your load arm, right, which is where the load is sitting, and the load force, which is the weight or the force the load, the object you're trying to lift, is applying to the lever. You also have the fulcrum, which is the turning point. So how can you tell how effective a machine is at reducing the effort required to move an object? Well, this is called a mechanical advantage, right? So mechanical advantage, or MA for short, is used to tell you how effective a machine is as reducing the effort needed to move an object. So mechanical advantage is calculated by load force over your effort force. Your load force over your effort force. So we can do an example, but we need to review what is load force. Load force, again, is the force the object is applying to your lever or machine. The effort force is the effort you put in, So, Austin needs to lift a 300 Newton object using only 100 Newtons of force. To do this, he uses a simple machine with a mechanical advantage of what? So again, we know some things, right? We know that the load force, or LF, right? The LF, load force, equals 300 newtons, right? Because it says this 300 Newton object. So the object is applying a force of 300 newtons. We also know that Austin is only going to use 100 newtons of force. So he's using that force, so that's your effort force. That's Austin's effort force, or EF for short. Right? So then we know that it's load force over effort force, right? Load force over effort force, 300 divided by 100. So the mechanical advantage of the machine is 3. That means that the machine is increasing the force that Austin is using by 3 times. It's making him 3 times more effective at lifting whatever object this is. So another example we could do is if you apply an effort of 240 newtons to a simple machine, and the machine has a mechanical advantage of 3, what is the load force? What is the load force? Well, the load force is the force applied by the object. The effort force is what we're applying, so we're applying 240, and the mechanical advantage is 3. So we know that MA, right, MA equals load force, so we have our load force, so we'll put LF over our effort force, which we know is here, 240. Right? We also know our MA, because the question's giving us that MA. The MA is 3, so we'll erase that and put the 3 there. Once again, this is basic algebra. I want LF by itself. That's what I'm looking for. So I have to get rid of the 240. I'm dividing by 240. So then I just times it by 240, which cancels it out. But whatever I do to one side, I do to the other side. So I times this by 240, which means I have a load force of 720, right? So basic algebra in this calculation will allow us to find the load force of the object. So there's another way to calculate mechanical advantage. You could do one, which is load force over effort force, But you can also do effort arm over load arm. Another way to call this is input arm over output arm, but they're the same thing. So you could calculate mechanical advantage in levers using load force over effort force, or effort arm over load arm. So effort arm is the arm you're applying your effort force to, right? So in a class 1 lever, it's this because the effort's on this side. In a class 2 lever, now this is where it gets a bit tricky because some people make, mistakes on this part. The effort arm is this fulcrum all the way to the effort, right? Fulcrum all the way to the effort. So in a class 2 lever, it's all the way to the other end. But the load arm, if I were to talk about the load arm, is the fulcrum to the load. So you can already see that why class 2 levers increase the force by a lot, or multiply your effort by a lot, because your effort arm is always larger than your load arm. And in the class 3 lever, the effort arm is here, and the load arm is way over there. Right? The load arm is way over there. So let's take a look at this again. Effort arm, fulcrum to the effort. Load arm, fulcrum to the load. Load arm is fulcrum to the load, but again, in class 2, the load and effort are on the same side, so it goes about this way, while the effort is much longer. The opposite is true for a class 3. The load arm, sorry, that's a mistake. The load arm is much longer. So it's about that long. All the way from the fulcrum to the load, while the effort is from the fulcrum to the effort force. Right? So you can calculate mechanical advantage using effort arm over load arm, or load force over effort force. This is a mistake you're going to make. Right? I'll give you a question that gives you load force and effort force, and you can calculate mechanical advantage. But then I might give you a question that gives you effort arm and load arm. And so you'll need to know that when I'm giving you the forces, and I'm saying find mechanical advantage, it's load force divided by effort force. But if I give you a question with the distance of the arms, it's effort arm over load arm. It's upside down. It's not load arm over effort arm. It's effort arm over load arm. And for when I give you forces, it's load force over effort force. So having a mechanical advantage greater than 1 means the machine multiplies the effort force by the MA. So if you have a mechanical advantage of 2, that means the machine has increased your force by a factor of 2. It multiplied your force by 2. Having an MA of 1 means the machine can change the direction of the load, right? A mechanical advantage of 1 means you could have lifted the object and it would have taken the same amount of effort. But in certain situations, and depending on the type of machine, the machine allows you to change the direction of the load. Having a mechanical advantage of less than 1 means the machine increases the speed of the load. So if you have a mechanical advantage of 0.5, that means that you're increasing the speed by 2, not the force or the effort by 2, right? So a mechanical advantage of 2 means that the machine multiplied your force by 2. Having a mechanical advantage of 0.5 means that the object is moving twice as fast. So a construction worker uses a board and log as a lever to lift a heavy rock. If the effort arm is 3 meters and the load arm is 0.5 meters, what is the mechanical advantage of the lever? So again, a mistake you'll make is instead of doing effort arm over load arm, you're going to do load force over effort force. But keep in mind, we are using meters. We're using the arm. So it'll be effort arm over load arm, which would be 3 divided by 0.5, right? And so 3 divided by 3 divided by 0.5 is 4. So we have a mechanical advantage of 4. In this case, we have a lever used to lift a heavy box has an input arm of 4 and an output arm of 0.8. What is the mechanical advantage? What kind of lever is this? Well, we have an input arm of 4 and an output arm of 0.8. So again, we go input, which is the same as effort. So 4 divided by 0.8 equals 5, right? So we probably have a class 1 or class 2 lever. So we're going to do a couple more practice questions on these. It's important to know the type of levers. It's important to know what mechanical advantage is, and it's important to know how to calculate it. Hopefully this was helpful, and I'll see you next lesson.